So thermodynamics is what we're talking about in this. Thermodynamics is the study of energy and its interconversions, how the energy goes from one form to another, how it goes from one object to another. And there are laws of thermodynamics. The first, what's known as the first law of thermodynamics, is the law of conservation of energy, which one way to state it is the total amount of energy in the universe is constant. You may have heard about perpetual motion machines, and people think they come up with something that's just this energy generator. There's no such thing as a perpetual motion machine, something that will keep moving without taking in any energy. People thought they had something, but it's just because they didn't understand all the forms of energy, and you study them more closely and you realize, oh, well, this is actually getting energy from the sun or something like that. So you can't design a system that will produce energy without taking in some source of energy. So here's this picture again, just to remind, and this is a very important concept that you need to remember when we get into solving some of these problems. Whatever's lost by the system is gained by the surroundings. So that means the sum of the energy changes. If you take the energy change of the system and add the energy change of the surroundings, it has to add up to zero. There's no net gain of energy, there's no net loss of energy. And so mathematically we can say it this way: delta is our symbol for change, and delta always means the final minus the initial. In many of these calculations, the sign matters. Whether it's positive or negative can matter a great deal, and so it's always final minus initial. So the change in energy of the universe, meaning the change, what you end up with minus what you started with, is always going to be equal to zero. The change in energy of the system plus the change in energy of the surroundings is going to add up to zero. So if your system gained 5 joules of energy, that means that the surroundings lost 5 joules of energy. Losing energy is negative, gaining energy is positive. So you've got plus 5 minus 5 adds up to 0. So internal energy, this is the energy of a system. It's the sum of all the kinetic and potential energies that the particles in that system have together. It's the energy of the system. Now, it's very, very hard to measure an absolute level of energy, because what do you compare it to? And so I don't think we're ever going to measure, at least in this class, the actual amount of energy that a particular system has. We're going to look at the change in the energy. We can measure that, but we can't measure this is how much energy something has. So the change in energy is what we're interested in. The change in energy depends only on the amount of energy in the system at the beginning and the end. So the internal energy is the energy of the system, and the change in it depends on where it started and where it ends. That's all. It does not depend on how it got there. Now, we haven't talked about state functions, have we? After a while, all these different chemistry classes kind of blur together, and I'm like, I think I remember talking about state functions with these people. But no, I didn't. So that's why I ask you. So, a state function. State function depends only on the initial and final conditions, not on the process used. Yeah, there is a picture. We'll get to that in just a minute. So we talk about change in energy. That means the final amount of energy minus the initial amount of energy. Always final minus initial. If we talk about the change in energy of a reaction, this is how chemists abbreviate the word reaction, RXN. That's the energy of the products minus the energy of the reactants. Because you start with reactants, you go to products. The change is the final, what you end up with, minus the initial. Let's look about the state function. So here's a mountain. I actually saw a weird-shaped pointy mountain like this on Sunday. Like, wow, that's kind of strange, because most of our foothills around here are really rounded on the top. But here's this mountain. Obviously, those people are not drawn to scale, because this is going from 0 to 10,000 feet. Okay? So there's two paths up this mountain. You can go this windy path that is 12 miles long, and you can get to the top. Or you can take this path, which is 5 miles long, but goes straight up the side of the mountain. Your change in elevation, your change in altitude, is a state function. It doesn't depend on how you got there. So the distance that you traveled is not a state function. These people on path A traveled 12 miles to get here. That was the distance they hiked. People on path B hiked 5 miles. But the change in elevation is the same for both of them. They started at 0, they ended up at 10,000 feet. The change in elevation is 10,000 feet, regardless of how you got there. Okay? So that's what we mean by a state function. State functions are nice because we don't have to really consider the process. It doesn't matter. We can measure the end result and compare it to the initial result, and we can figure out how it has changed. And we don't care exactly how that happened. It doesn't matter. We're going to use energy diagrams. A lot of chemistry is very abstract. I'm a visual person. I need to be able to see things. A lot of people are visual learners. And so these graphs and diagrams can be real helpful to get a mental picture of what's going on with these things. So we use these to show how the energy is changing in a process. So here's an example reaction. Here we have carbon dioxide decomposing to form carbon and oxygen gas. Well, what we're going to do here is we're going to show internal energy of the system as increasing going up. So this is a little like a graph, and yet we're not that concerned with numbers. We're just concerned with relative positions. And here we see that the energy of the products is higher than the energy of the reactants. So in the process of this reaction occurring, carbon dioxide changing into carbon and oxygen, the system, which is the reactants and products together, have gained energy. The internal energy has gone up. So the change in energy is greater than 0. It's positive. The system gained energy. I gained money. It's positive. I feel positive about that. So energy coming in is a positive thing. Where did that energy come from? It came from the surroundings. If the system gained energy, the surroundings must have lost energy. So the surroundings transferred energy to the system. The energy of the system is positive because it gained energy. The energy of the surroundings is negative. Okay? Because if you give me money, that's positive for me and that's negative for you. Right? If we flip this reaction around and we swap the reactants and products and say it's going the other way, that the carbon is reacting with oxygen to form carbon dioxide. This is what happened when you had all that black soot on your crucibles the other day and you heated it and it kind of magically disappeared, right? You were transforming carbon into carbon dioxide, which then floats away. Well, here the reactants have a higher internal energy than the products do. And so this is a reaction in which there is a loss of energy by the system. So the system is losing energy and the surroundings are gaining energy. If something loses energy, it has to go somewhere. You know, it's like money. You lost a $5 bill. Did it cease to exist? No, maybe you don't know where it is, but it came out of your pocket, and it's either sitting on the ground somewhere or someone else found it and picked it up, but it still exists, right? And so sometimes when we have these things where it appears that energy is lost, it's just that we haven't found it yet. It's still there. So whatever is lost by the system is gained by the surroundings. Whatever is gained by the system is lost by the surroundings. So energy flowing out of a system, it all flows into the surroundings. And again, the system is whatever we define it to be. Energy flowing out is negative, energy flowing in is positive. And since all of the energy from the surroundings and the system are just going back and forth to each other, that means the energy of the surroundings is equal to the energy of the system. It's just the sign is different. Because whatever the system loses, the surrounding gains. So the number, the magnitude of the energy is the same, only the sign changes. And what the sign is depends on what you define as the system and the surroundings. So it's like money in your checking account or in your wallet. Energy leaving is negative, energy coming in is positive. And I've said that many, many times, but I say that for a reason. Because we need to keep that straight, okay? Because we will have to be keeping track of, is this energy change negative or positive? So it's just like money. It's just like money. So energy can be exchanged in different ways, through heat and through work. And these are different things. Remember? Heat is the flow of energy due to a temperature difference. Work is applying a force across a distance. So these things are different. Now, the change in energy is a state function. It doesn't depend on the process. But heat, which is given the symbol Q, don't ask me why, I don't know. Maybe because H was used in many other places. W is for work, that makes more sense. These are not state functions. Their values do depend on the process. But the change in energy of something is equal to the sum of the heat and the work. So together those add up to the change in energy. So conventions of signs. Q is heat. If the system gains thermal energy, that's positive. Energy coming in. If the system loses thermal energy, if it cools off, that's negative. Work. This one's a little harder to relate to money, but think of work, someone doing maybe a massage, okay? People get paid to give massages, right? So if someone is massaging you, they are doing work on you. Is that a positive thing? Yeah, that's a positive thing. If work is done by the system, if you are doing the work on something else, is that fun? No, not really. Right? So that's negative. The overall change in energy going into the system is positive, like money coming into your wallet. Energy flowing out is negative. So you could have positive Q and negative W, and how they add up depends on how big they are. Both Q and W could be positive, both Q and W could be negative. We've got different possibilities there. So here we've got a smooth pool table. Here this white cue ball has an initial kinetic energy of 5 joules. As it rolls across the table, it is slowing down a little bit because of friction. There is heat energy being lost, so 0.5 joules is being lost as it rolls across the table. And we know that eventually the pool ball, even if it doesn't hit anything, it would stop, right? When it collides, there's a transfer of kinetic energy, and this cue ball stops. Its remaining kinetic energy is transferred to the purple ball, and so there's 4.5 joules of energy transferred. So we say the work that is done is negative 4.5. The system we're talking about here is the white ball. We're defining this in terms of the white ball. The white ball did work on the purple ball. The work was negative 4.5 joules. The heat, the energy was lost, so that is also negative. So overall, the change in energy for the white ball, the system, is negative 5.0 joules. So delta E is negative 5. It started out with 5 joules, now it has 0. The surroundings gained 5 joules of energy. The table gained 0.5 of thermal energy from the friction, and the purple ball gained 4.5 joules of kinetic energy. Does that make sense? This is how we think about energy. What if we have a rough pool table? So I think we know that, if you roll a ball across cement, it's going to roll a lot faster than if you roll it across long grass. There's more friction on a rough surface. So if we do the same thing on a rough table, the ball has the same amount of initial kinetic energy, 5 joules. As it rolls across now, there's a lot more friction, and so 3 joules are lost to heat. And then at the collision, there's only 2 joules of kinetic energy left to be transferred to the purple ball. So the work that's done is minus 2 joules hitting the other ball. Q is minus 3 joules. Overall, the change in energy is the same. The process is different from the first smooth table to this rough table, but the change in energy is a state function. It doesn't matter how it happened. W and Q are not state functions. Any questions? Delta E is the same. The white ball lost 5 joules of energy. The rest of the universe, which here is mainly the pool table surface, and the purple ball gained 5 joules of energy. So delta E for the white ball is the same on both the rough and smooth table, but the Q and the W are different. Delta E is a state function. Q and W are not. Yeah, I basically said all that. But the sum of Q and W is the same, even though the values of each are different. So heat's the transfer of thermal energy, and it occurs when there's a difference in temperature. So there's thermal energy, which is a form of kinetic energy. It's the particles moving within the substance. Heat is the transfer of that thermal energy, and temperature is a measure of thermal energy. We've got these 3 terms, and they are very similar, and so we need to try to keep them distinct and understand what each of them is. So heat is going to flow from matter with a high temperature to matter with a low temperature until they reach the same temperature, and that's called thermal equilibrium. So we know this experimentally. If you put a hot potato and a cold burrito in a lunchbox together and you leave them, what's going to happen? The potato's going to cool down and the burrito's going to warm up, and they're going to eventually reach the same temperature, right? That's what happens. Because heat flows due to that temperature change. Once the temperatures are the same, there's no additional net transfer of heat.